Alright, we'd like to talk a little bit about wave mechanics. So when we said we talked about mechanical waves, there were two types of waves. We had what were called longitudinal waves, and we also had transverse waves. So let's talk about, first of all, the transverse wave. So let's say you have a spring, and then you sort of fix it to a wall. You grab one end, and then you start to move your wrist up and down. So you kind of have something looking a bit like this. So here's the spring. You kind of move your hand up, and then the spring is attached to the wall. So what's going to happen is this piece here, it's going to start to move towards that wall. But your hand's moving up and down, so this is the motion of your hand. So you're kind of moving it up and down to create this thing called a wave pulse, and the energy disturbance is going to go this way. So this is a special scenario. So if we find that the direction of the energy transfer or the wave pulse, if its direction happens to be perpendicular to the disturbance, so my hand moving up and down is perpendicular to this direction of propagation, this is what we refer to as a transverse wave. So to remember the whole perpendicular part, I like to think of the letter T like an uppercase letter T, and kind of how the top part and the vertical part, they make a right angle. That's my way of remembering that the direction of propagation and the direction of disturbance are perpendicular in a transverse wave. So common examples of transverse waves, in Physics 30 you'll learn that all electromagnetic waves are transverse. Those of you that play musical instruments like a guitar, you're going to pluck the string. That is an example of a transverse wave. So a longitudinal wave is a little bit more special. So a longitudinal wave, what's going to happen is you're going to kind of, for example here, let's say I have this slinky. Let's say I kind of pull it back and then let go. What's going to happen is the slinky is going to kind of oscillate back and forth in this horizontal plane. You'll also notice that the pulse is going to travel in this horizontal plane. So you might see the wave pulse, the energy transfer just going through this way. So in that case, where the transfer of energy and the disturbance are in the same plane, they're parallel or anti-parallel, these are referred to as longitudinal waves. Longitudinal waves don't get a lot of attention in high school. I don't know why. They are a little bit trickier, but they are still very common. Like one of the best examples of longitudinal waves that we have is sound. Sound's also referred to as a pressure wave, because what's happening in sound, like let's say we kind of have the still air here. I'm just kind of sketching this, and here's your ear. That's a really bad ear. But basically what's happening is, like, if I produce a sound, like, I kind of speak, well, now these air molecules, they're going to oscillate back and forth. They're going to transfer their energy to the next molecules. They're going to oscillate back and forth. Then these molecules next to them are going to oscillate back and forth. And then that's just going to continue until we get to the ear. So these are going to continue to oscillate back and forth. And then once we get in the ear, that energy that's been transferred to all these molecules, it's going to hit the eardrum. That eardrum is going to oscillate back and forth. And then your brain, that lovely organ, it is going to interpret that oscillation as a particular sound. So we notice that these oscillations are parallel and to the direction of propagation. So this is a longitudinal wave. So all sound is that you hear, like you hearing my voice right now or listening to somebody talking to you, it's just air molecules oscillating back and forth in a parallel plane to the direction of propagation. And it's just a transfer of energy. That's really all it is at the end of the day. It's kind of neat that that's all sound happens to be. Now let's look at this thing called the universal wave equation. So we've talked about in the last couple units, we've talked about the time it takes to complete a full cycle, or in our case, to use the wave terminology, a full wavelength. We call this the period. So we could develop the following equation. We could say this lambda equals Vt. So this is kind of similar to like d equals Vt. So we have the speed of our wave, the time to make a full cycle is the period, and that distance covered in a full period is this lambda. We also know that t is equal to 1 over the frequency. So we could certainly take this relationship here and put it into there. So what we do is if we combine those two equations, we get this lambda equals v over f, or we'll see this written as v equals f lambda. So in this equation, v is going to be the speed of our wave in meters per second, f is going to be the frequency in hertz, lambda is going to be the wavelength of the wave. This is known as the universal wave equation. This equation is on your data sheet. It works for any wave, hence the name universal. So it works for mechanical waves, It doesn't matter if they're transverse or longitudinal, and they also work for electromagnetic waves that you'll talk more about in Physics 30. All we do with an electromagnetic wave is where we have v here, that's set for an electromagnetic wave. So we're going to switch that to c, the speed of light. So in Physics 30, you'll see something like this, c equals f lambda, because this is an EMR wave. Electromagnetic radiation wave. So let's look at an example here. We'd like to find the speed of a wave with a frequency of 1.8 megahertz, and it happens to have a wavelength of 35 meters. All right. So we have our universal wave equation. We know v is equal to f times lambda. We don't like the megahertz, but we know mega is 10 to the 6. So the frequency is 1.08 times 10 to the 6 hertz. And we have a wavelength of 35.0 meters. So this is probably some type of radio wave, just based on the frequency and the wavelength given. Well, actually, it can't be a radio wave because this isn't going to come out to the speed of sound. So what kind of wave this is, who knows. What we are going to find is we're going to get the speeds about 3.78 times 10 to the 7 meters per second. All right, one thing I do want to comment on before we move on, though, when we talk about calculating speeds, think of the speed of light as kind of like the universal maximum speed limit. None of your values of speed should ever exceed this. If your speed exceeds the speed of light, you did something wrong and you need to fix that. This is the fastest we can go, so your answers should never exceed that. Just something to be aware of. So let's look at another little more complicated example. Let's throw some kinematics in there just for good measure. So we're going to have a person, they're going to approach a wishing well. They're going to find a penny in their pocket, so you know the old 1-cent piece. So they're going to toss this down the well, which happens to be 50 meters deep. So the sound wave has a wavelength of 2.76 meters and a frequency of 125 hertz. So let's determine the time it will take for the person to hear the penny hitting the bottom of the well after they release the penny. All right, so this question has a little bit going on there. So there's kind of two parts. So I'm going to sketch my little well here. Okay, I don't know what I'm doing here. This is kind of fun. Okay, so this is kind of an ugly looking well. That's really bad drawing. Okay, my well kind of just changed width. Bear with me, I'm no artist. So there's kind of two parts. We want to find the time after the penny's dropped. So first of all, this person here, they're going to drop the penny. So we're going to have to find the time it actually takes to drop. Now, what's going to happen is the penny is going to hit the ground and it's going to make a sound. So then these sound waves are going to make their way up to the top of the well. So we need to find two times. How long is it going to take for the penny to actually get to the bottom of the well? And then how long is it going to take that sound wave to propagate from the bottom of the well up to the top? So we're going to call this first, second. So part one. So the time for penny to fall, 50 meters. Now this is a classic kinematics question. And for this we'll call down positive. So what do we know? We know the acceleration is positive 9.81 meters per second squared. We're dropping it, so we're going to assume VI is 0. We know the distance is 50 meters, and we'd like to find the time. So we need an equation that has A, VI, D, and T. So D equals VIT plus half AT squared is going to come to the rescue. And we always love this equation when we're dropping something because the whole VI part goes away. So we have D equals half AT squared. And we have rearranged this one quite a few times, so we could say that T is equal to the square root of 2D over A. So we have 2, and then we have that distance of 50 meters divided by the acceleration, 9.81 meters per second squared. So this is going to give us, what are we getting here? We're going to get about 3.193 seconds. So the first step here, when this person drops the penny, and I'm going to call this T1 because this is the first time. So when this person drops the penny, it's going to take about 3.19 seconds for it to actually hit the bottom of the well. Now that it hits the bottom of the well, a sound wave can propagate. So we're going to find the time for sound wave to reach top. So because this is a wave, now for wave mechanics, we always are allowed to use v equals d over t because waves don't accelerate. Waves allow us to use uniform motion. We know the distance, we don't know the time, or sorry, we're trying to find the time. So time is going to be the distance divided by the speed. Now, we don't know the speed, but we also know for waves, v is equal to f lambda. So we can plug that in there. You could calculate the speed first. That certainly could work. So we know that we have this distance that this has to travel divided by the frequency times the wavelength. So this thing is going to travel 50 meters. This wave, we're told, has a frequency of 125 hertz and a wavelength of 2.76 meters. So we're going to call this time 2. So the time it's going to take for the sound wave to reach the top of the well, it's going to be about 0.145 seconds. So you figured out probably quickly that sound travels quite a bit faster than, the penny. So this is the time it takes for sound wave to travel from the penny where it's generated to the top of the well. So the total time that we need for this question is the time it takes to drop plus the time it takes for the sound wave to propagate. So if we put those two pieces together, we're going to get about 3.34 seconds. So based on this information, we're going to say that it takes after the penny gets dropped, it's going to take about 3.34 seconds for the person to be able to hear the sound that penny makes hitting the bottom of the well. Right, let's determine the frequency of violet light if the wavelength is 400 nanometers. So violet light is electromagnetic radiation. So if you're asked to find frequency, we know v is equal to f lambda, and we're given wavelength, but we're not given speed. In those cases, if you're not given speed and you need it, it's probably an electromagnetic wave. So this is an EMR wave, which means that the speed is the speed of light. So really, we have the speed of light is equal to the frequency multiplied by the wavelength. So we're going to divide both sides by the wavelength. So we're going to get the frequency is this speed of light divided by the wavelength. So we have the 3 times 10 to the 8 meters per second. And then we have a wavelength of 400 nanometers. Nano is just 10 to the minus 9 meters. So we have 400 times 10 to the minus 9. Or if you want to write it with proper scientific notation, you could write 4.00 times 10 to the minus 7. For calculations, who cares how you write it? That's not a big deal. So what we're going to get is we're going to get about 7.50 times 10 to the 14 hertz. Now, when we talked about frequency, we said that's how many complete cycles of the wave approach every second. So what this is saying is that for us to interpret violet light, we need something that's traveling at the speed of light, and we need about 7.50 times 10 to the 14 complete cycles of that wave to hit our eye every single second. That's what we mean by frequency. So again, with these questions where we're dealing with EMR, if you're not sure if it's EMR, like if you're asked to calculate frequency or wavelength, you're given the other, but you're not given speed, chances are it's an electromagnetic wave. So last thing we just want to talk about here, we're going to start to lead into the case of what happens when we go between different media. So like going from air to water or oil to air. So when a wave travels from one medium to another, one of its properties stays constant, and that is the frequency. The frequency of a wave does not change as it travels between media. There's a really advanced explanation for that. The high school level one, we're going to keep it simple. Frequency is only dictated by the source. So whatever produces that wave is going to govern its frequency. So for example, if I shine a green laser pointer into some oil, in the oil, the wavelength of light is going to change slightly. But the frequency will not change. The fact that the green light enters oil doesn't change the fact that I originally shone green light. Like, it's still green light at its source. So frequency always stays constant. Now, in my equation V equals F lambda, if this gets to stay constant, that means when we go between media, V and lambda are going to have to change. Now, if we happen to enter a medium that is more dense than the previous medium, what's going to happen is the wavelength is going to decrease. We almost want to think of it kind of getting squished. Nature is going to respond to this by decreasing the speed of the wave. So as a wave enters a more dense medium, it's going to slow down, and a consequence for it slowing down is that its wavelength is going to decrease. So V goes down, lambda goes down, and of course frequency is constant. We can also do the other case. If we go from a dense medium to a less dense medium, the wave is going to speed up because there's not as much kind of getting in the way in terms of density of that material. So the wave is going to speed up. If the wave speeds up, by consequence, what we can also say is that the wavelength increases. And then, of course, the frequency is constant. Now, this is something that we'll study a lot more in Physics 30. You'll also notice because we have a change in velocity when we go between media, you're also going to have a change in direction. So this is also why, like, if you dip a pencil in water, it looks like the pencil's bent. Or if you're ever in a swimming pool and you're trying to grab something off the bottom of the pool and you're like where you try to grab is not where the object actually is, it has to do a bit with a bending of the light rays themselves. And this is what is known as refraction. But refraction is something we'll talk more in Physics 30. We'll save that surprise for next year.